Today we're going to be talking about radioactivity. So the first thing we want to understand is, what do we mean when we say that an atom is radioactive? And when you hear the term radioactive, what you want to think about is unstable. So a radioactive atom is unstable, and therefore it has to figure out a way to become stable. And the way it does that is it will emit radiation. And in order to become stable, it emits radiation. We want to talk about what are the different types of radiation that it can emit. And this will be one of the principal things that we talk about in this PowerPoint. So it turns out that there are three types of radiation that can be emitted by a radioactive atom. And those are called alpha, beta, and gamma rays. And we will go through each of those in quite a bit of detail. In terms of where does radioactivity originate inside the atom, it turns out that radioactivity originates in the nucleus of the atom. So it doesn't involve the electrons surrounding the atom. It all occurs, or radioactivity is all created in the nucleus. Just some vocabulary. We use the term nuclide to represent a type of atom whose nuclei have specific numbers of protons and neutrons. And let me show you what I mean by that. For example, we know that most elements have different isotopes. And if you remember what an isotope is an element that has different numbers of neutrons. So, for example, three common isotopes of carbon are carbon-12, which is 6 protons and 6 neutrons, carbon-13, which would be an additional neutron, and carbon-14, which has 2 additional neutrons. So each of those would be a different nuclide. Okay? So a specific number of protons and neutrons. So carbon-12 would be a different nuclide from carbon-13. Now, it turns out that some nuclides are radioactive, and we call these radionuclides or radioisotopes. And that simply means a nuclide that is radioactive. So, continuing with the example from above, carbon-12 and carbon-13 are not radioactive, but carbon-14 is. So carbon-14 would be an example of a radioisotope or radionuclide, simply meaning it's an isotope that's radioactive. Let's talk about what causes radioactivity. And before I get into that, let me just explain the graph that's on the slide. First of all, you'll notice that this is simply a graph of the number of protons in the nucleus versus the number of neutrons. And you'll notice that we have two different colors here, pink representing radioactive nuclides, and blue representing non-radioactive or stable nuclides. So one of the things you'll notice is that when we're low down in terms of the number of protons and neutrons in an atom, for the nucleus to be stable, we want about the same number of protons and neutrons. But as we get to bigger and bigger nuclei, we need more and more neutrons to make that nucleus stable. And if we have an imbalance, or we don't have the right mix of protons and neutrons in the nucleus, then that nucleus will be radioactive. So what actually is causing that? Well, it turns out that there are two different forces acting in the nucleus, and if we don't have the right mix of protons and neutrons, then we get an imbalance between those two forces. Let me tell you about what the two forces are. The first one is a force that you're familiar with, which is just the electrical force. We know that like charges repel and opposite charges attract. So if you think about inside the nucleus, we only have positive charges. We have protons, which are positive, and then of course neutrons don't have any charge at all. So the electrical force between the protons in the nucleus is repulsive. It's trying to blow the nucleus apart. Therefore, there must be another force that tries to keep it together, and that's called the strong nuclear force. And that acts among protons and neutrons, and it's attractive. And it turns out that as we get bigger and bigger nuclei, as we add more protons and neutrons, we simply need more neutrons to keep that nucleus together. And so that's why the stable nuclei curve down like this. And again, if we have the wrong balance, too many protons or too many neutrons for a given nucleus, then that nucleus is radioactive. And as we said, if it's a radioactive isotope or radioisotope, it will try to become more stable by alpha, beta, or gamma decay. Okay, so let's start looking at what we mean by alpha, beta, and gamma decay. And we'll start out with beta decay. In beta decay, one of the neutrons in the nucleus transforms into an electron and a proton. And so here's our original nucleus here. What happens is one of the neutrons becomes a proton and an electron, and the electron is emitted from the nucleus. And so what we're left with is a different nucleus than what we started with, because it now has one more proton than it did originally. You'll notice though it lost a neutron, so the number of nucleons stays the same. So you'll notice that if we start out with thorium-234, meaning it has 234 protons and neutrons to start out with, what we end up with still has the same number of protons plus neutrons, but it gained a proton and it lost a neutron. And therefore, it's a different element, because remember, it's the number of protons that determine the element. Okay? So in beta decay, Z goes to Z plus 1. In other words, we add a proton, but A stays the same. Okay? The total number of nucleons stays the same. By the way, this symbol beta here, that's just the symbol that we use for an electron. So just to summarize that, when we have beta decay, a proton or a neutron changes into a proton and an electron. The electron is shot out, that's the radiation that's given off, and the remaining nucleus is now different than it was before. Let's try a couple examples and see if we can figure out what would the decay product be, or sometimes referred to as the daughter nucleus. So if we start out with Pa-234, if it's undergoing beta decay, again what happens is the number of protons goes up by 1. Okay, so that goes up by 1. But the total number of protons plus neutrons doesn't change. And so we would have 234, but now we'd have 92 on the bottom, and that turns out to be uranium. So if you had a periodic table, you could just look up and see what element is it that has 92 protons. Just to do another one, if we start out with Pb, which is lead, 82, we would increase that by 1 because we gain a proton. Number of protons plus neutrons doesn't change, and if you look that up on a periodic table, that's Bi or bismuth. Okay, so those are a couple examples of beta decay. And again, this represents the electron being given off, and that's what we mean by the radiation being given off. Let's take a look at alpha decay. Alpha decay is similar to beta decay, except instead of a proton changing into a neutron, or a neutron changing into a proton as in beta decay, what happens here is a chunk of the nucleus is given off. And an alpha particle is just a helium nucleus. You may remember that helium is the second element in the periodic table. So helium has 2 protons and 2 neutrons. Okay, so that's why we have a 2 down here and a 4 here. And so that's what we mean by an alpha particle. So an alpha particle is actually a helium nucleus. So here we can see uranium-238 undergoing alpha decay. It loses 2 protons and 2 neutrons. That's what's being given off. And therefore, what it ends up with is something that has 2 fewer protons, so Z minus 2. and 4 fewer nucleons, because it loses 2 protons and 2 neutrons. Okay, so that's alpha decay. And again, you'll notice that we're ending up with a different element than what we started with. All right, let's take a look at an example of alpha decay and see if we can figure it out. So let's say we start out with thorium-234. Now let's see if we can figure out what we would end up with when it undergoes alpha decay. Well, it's going to lose 2 protons, so we've got to subtract 2 protons, and it's going to lose 4 total nucleons, so we would end up with 230 here. And if we looked up 88 on the periodic table, we would see that's Ra, which is radon. Another example, if we take radon, turns out that's radioactive as well, and that would decay. That would become 86, because again we'd lose 2 protons, and the top number would become 226. And if you look that up on the periodic table, you would find that's Rn. Right? So that's what alpha decay looks like. So now that we've seen what alpha decay is and what beta decay is, let's compare these two different decays. So it turns out that most radioisotopes will undergo beta decay, and only the heavy radioisotopes, so larger nuclei, will undergo alpha decay as well. And you can kind of see why that is. In alpha decay, you lose a big chunk of the nucleus, and so only bigger nuclei have that much to give up. The important thing too to understand here is that that alpha particle, which is a helium nucleus, and this electron, that's what we mean by radiation being given off. So the new nucleus just stays where the old nucleus was in each case, but that helium nucleus or that electron are shot off with a lot of energy, and that's the radiation. Okay, so both types of decay emit radiation in the form of a particle, and both types end up with a new element from the element you started with.